In this, we are going to learn what we call the constant coefficient linear homogeneous differential equation. So what we try to do, constant coefficient linear homogeneous equation. Differential equation, but in short we just call it constant coefficient equation, but you have to be careful, it has to be linear and homogeneous as well. So so this kind of equation has this form, so has the form a y double prime plus b y prime plus c y equals 0, where a not equal to 0. That's the first thing, because otherwise actually here we focus on the second order, so we assume that a not equal to 0, and also a, b and c are constants. Okay, so that is the equation we're going to focus on first, and then also a little bit of theory here. Any two solutions y1 and y2 that are linearly independent, is called a fundamental set of solution, is called a fundamental set of solutions. Fundamental set of solutions. So it's very important. So because it's second order, that means there should be two solutions, but if the two solutions are linearly independent, we call it is a fundamental set of solutions. And then the general solution is given by y equal c1 y1 plus c2 y2, where c1 and c2 are any constants. Good. So that's the major theory part. So we call any two solutions that are linearly independent are fundamental set of solutions. And then if you know this is a fundamental set of solution, then we can write the general solution as y equals c1 y1 plus c2 y2. Now the question is how to solve this differential equation. Like if you have a constant coefficient differential equation, how to solve it. So what we can do, we know that, like for example, if you assume a solution of the form let's say e to the lambda x, if you assume a solution of the form e to the lambda x, when you take the derivative, what will happen? The lambda comes out. So and then you can see that the e to the lambda still stays there in that same form. So that means that maybe your solution has that special form. So what we can do, we can assume the form of the solution, and then we're going to plug in there and solve. So that's how we're trying to do. So let's do that. So the question how to solve. So what we're going to do, we're going to assume. So try a solution of the form y equal e to the lambda x. Lambda is a number that we don't know, it's unknown, but we can assume that the solution has this form The reason is why we assume this kind of form is we know that when you take the derivative of e to the lambda x, e to the lambda x stays there. So that term stays there. I mean, we can use that fact. Okay, so let's see how the rest of the thing works. So what we can do, we get a derivative. So the first derivative is, if you take the derivative by the chain rule, it is lambda e lambda x. And if you take the second derivative, it is, you get one more lambda, so lambda is squared e to the lambda x. So you can see that e to the lambda x is there. Now what we can do, we can substitute that to the differential equation. So we substitute into the differential equation into a y double prime plus b y prime plus c y equals 0. We're gonna get for the first term we're gonna get a lambda squared e to the lambda x, and then plus from the second term we're gonna get b lambda e to the lambda x. From the third term we get c e to the lambda x, which is equal to 0. Now you can see that e to the lambda x is common, so we can take a lambda squared plus b lambda plus c, and then e to the lambda x equal 0. Now we know that e to the lambda x is never 0. So since e to the lambda x not equal to 0, the only thing that can happen is the one in the parenthesis has to be 0. So we see that a lambda squared plus b lambda plus c equals 0. So this is what we get, and this is what we call the characteristic or the auxiliary equation of the differential equation. So this is called the characteristic this is called the characteristic equation. This is called the characteristic, or some people call it auxiliary equation. The characteristic or the auxiliary equation of the differential equation. Okay. Good. So this is important, so we're gonna use this. And so what exactly happened is, you can see so wherever you see the second derivative, you replace by lambda squared. Wherever you see the first derivative, you replace by lambda. So that's exactly what happened, because we know that when you take a derivative, lambda terms comes out. So you can just simply generalize this result even for higher order derivatives, higher order differential equations. Simply replace wherever you see a derivative by a lambda to that power. It's a second order term, then the lambda square is a first order term, lambda to the 1. If it's a third order term, lambda to the cube, like that. So but this equation is what we call the characteristic equation. So you can simply write this equation if you have a differential equation. Good. Now, so this is a you can see is a quadratic equation in lambda. So this is a quadratic equation. This is a quadratic equation in lambda. So we can use the quadratic formula to solve it. So let's do how we can do the rest. So what we can do, solve for lambda by factoring or using the quadratic formula, by factoring or quadratic formula. By factoring or using the quadratic formula. you can either use the quadratic formula or you can just use the factoring technique. So that means you're going to get lambda 1 and lambda 2, which is given by negative b plus or minus b squared minus 4ac square root over divided by 2 to the 2 times a. So what we can do, you know that the depending on the discriminant, this is the discriminant is what we call the b squared minus 4ac. Depending on the sign of that, the three things can happen. So we know that if the discriminant is positive, then you have two real roots, two real distinct root, and then if the discriminant is 0, we're going to get two equal. You can say real, let's say real equal. So you're going to get they are both real and equal repeated roots. And then if lambda is negative, you're going to get complex conjugate. Complex conjugate root. So that's the case. So that means we have to consider those three cases separately, and that's exactly what we can do now. So let's consider one by one. So let's go with the case 1. So the case 1 is, we're going to say b squared minus 4ac is positive. That's the first case. So in this case, what's going to happen? So we have two real distinct solutions. Two real distinct solutions. We can call it lambda 1 and lambda 2. So we get lambda 1, one solution, lambda 2, the other solution. So then we have two solutions to the differential equation, because we know that the solution has the form e to the lambda x, and the lambda is coming from here. So that means we just need to plug it. Okay. So the two solutions are one is y1 equal e to the lambda 1x, and the other solution is lambda 2, which is e to the lambda 2x. Those are the two solutions. So that's the first case. Now let's look at the second case. So in the second case, what will happen? B squared minus 4ac equals 0. So let's do the case 2. So in that case, we have b squared minus 4ac, which is equal to 0. So that means we have repeated roots. So this means that we have real repeated roots, repeated solutions. We can call it lambda 1 and lambda 1. We write it twice just to make sure that it's a repetition, because it's important. And then this lambda 1 is simply given by the formula, so we can have lambda 1, which is given by, in the quadratic formula, b squared minus 4ac is 0. So you simply get negative b over 2a. That's the value. And the solution is simply y1 equal e to the lambda 1x. Lambda 1 is given by this formula. But the problem is how to find the other solution. So let's look at the differential equation now. So what we can do, we can look at the differential equation, and you can divide by a. So you can say the differential equation can be written in the standard form can be written in standard form, so we have y double prime plus, if you divide by a, it's a b over a, y prime plus c over a, y equals 0. Now what we can do, we already know one solution is e to the lambda 1x. To find the other solution, we can use the reduction formula that we discussed earlier. So let's use the reduction formula now. So if you use the reduction formula, so the second solution is given by the reduction formula, So what's the reduction formula? Which is y2 equal y1 and then e to the minus px dx divided by y1 square dx. Now what we can do, we're going to plug in here. So what happened, this is e to the lambda 1x, and then here e to the minus px is what? Px is b over a dx, and in the bottom we have e to the minus lambda 1 is b over 2a x, so to square this dx. Now you can see that this is simplifies very well. So what's going to happen, in the top it is e to the minus b over ax. In the bottom, when you square, that means you multiply the power by 2, that means you are getting e to the minus b over ax dx. And you can see that these two terms are the same, so they cancel each other. So that means you end up getting this is 1, so 1 dx, that means x, so that means your answer would be x e to the lambda 1 x. So that's the second solution. You simply multiply by x. So the two solutions are one is y1 e to the lambda 1x, and the other solution is y2, which is x e to the lambda 1x. So you just multiply by x, and then you can see that they are linearly independent, because you can look at the Wronskian, and if you look at the Wronskian, and you can see that it's never equal to 0, so they are linearly independent. And we also discussed that earlier in the reduction formula. The two solutions are linearly independent. We prove that that's the case. But if you want, we can check that. So we can look at the Wronskian. This is w y1 y2 which is y1 prime, y2 prime. So you're gonna get e lambda 1x and then lambda 1 e lambda 1x. The other one is x e lambda 1x. If you take the derivative, it is e lambda 1x plus, and then take the other one is a lambda 1 x e lambda 1x. Now if you expand this, you can see what's going to happen. A lot of terms get cancelled. For example, you multiply this with that, and then e lambda 1 times lambda 1x, but that terms you also get, so that means this simplifies simply to e twice lambda 1x. That's where you end up, and which is not equal to 0. So that means the two functions are linearly independent. So two functions are linearly independent. Two forms are linearly independent. So that happened. So that means we can write the general solution in this case as well, because we know the two solutions, so you can add them. So we can write the general solution adding the two. We are multiplying by a constant and adding the two. Good. So let's go to the third case. So that means this is a fundamental set of solution because these two are linearly independent. Two functions are linearly independent and form a fundamental set of solution. Fundamental set of solutions. Fundamental set of solutions. Good. So let's go to the third case. So case number 3. So in the case number 3, what will happen is b squared minus 4ac is negative. So if they are negative, what's going to happen? You're going to get two complex numbers, so you're going to get the solutions as complex. So you're going to get conjugate complex roots. That means in that case your solution you can write as lambda equal alpha plus or minus I beta form. So that's the solution gonna look like always like that in this case. So we can use this to find the solution. So the two solutions are you can write y1, which is e to the alpha plus I beta x, that's one solution, and the second solution y2 equal e to the alpha minus I beta x. So those are two solutions. Now what we can do, we can use Euler's formula to simplify this. Use Euler's formula. Use Euler's formula to simplify. So what's Euler's formula? It is e to the I theta equal cosine theta plus I sine theta. So let's use that. So let's try the general solution. So the general solution is y, which is c1 y1 plus c2 y2. So I'm going to plug it. We plug in into c1 e to the alpha plus I beta x plus c2 e to the alpha minus I beta x. Now what we can do, we can take e to the alpha x out. So if you do that, so you can write this one as c1 e to the alpha x, and then e to the I beta x, you can use the Euler's formula to simplify. That means you can write this one as cosine beta x plus I sine beta x. The second one also you can write this the same way. You can write this one as c2 e alpha x cosine beta x minus I sine beta x, because cosine is an even function. Okay, so that part's gonna give you that, this one gonna give you this. Now we can combine the two. So what we can do is we can go with e to the alpha x, the cosine terms first. So if you go with the cosine terms, you can write this one as c1 plus c2 e to the alpha x cosine beta x plus, now go the I terms. If you go with I is common, so you have c1 minus c2 e to the alpha x sine beta x. Now what we can do, we just call this this whole term just the abuser notation. I'm just gonna this whole, it's just a constant. I'm gonna call this constant C1. I'm gonna call this whole constant even with I C2, just a new C1 C2, because it's just a constant, it doesn't really matter. So with that notation, I'm gonna call this just a constant C1 e to the alpha x cosine beta x plus e to the alpha x, actually here we have C2, the constant C2, we have the constant C2 e to the alpha x sine beta x. So that's what happened in the complex case. The third case, you can write your solution in this form. So it is a good idea to put everything together. So let's put all of them together as one result. So let's call the theorem. So we have this result. So we're going to put everything together. So suppose lambda 1 and lambda 2 are two solutions. The two solutions of the characteristic equation A lambda squared plus b lambda plus c equals 0 of the differential equation a y double prime plus b y prime plus c y equals 0. Then the general solution takes a form. Then the general solution takes the form so there are a lot of solutions. So general solutions take the form. Let's go with one by one. First, if b squared minus 4ac greater than 0, in that case we have lambda 1 and lambda 2 are real distinct, real distinct. So the solution is y equal c1 e lambda 1x plus c2 e lambda 2x. That's the first case. The second case, if b squared minus 4ac equal to 0, then what happened? Then lambda 1 equal lambda 2. So what happened? Real equal. So in that case the general solution is y equal, there are two forms. One form is c1 plus c2x times e to the lambda 1x, or you can split this, you can write this as c1 e lambda 1x plus c2x e lambda 1x, like that. The third case, if b squared minus 4ac negative, this is negative, then what's going to happen? Your lambda can be written as alpha plus or minus I beta I. In that case the general solution, so these are a complex conjugate. So if the coefficients are real, this is always the case. You always get complex conjugate solution if the coefficients are real. So in that case, the solution has the form y equal e to the alpha x. You can write this as c1 cosine beta x plus c2 sine beta x. So that is the general form of the solution in the third case. So this is a very powerful result, and we can use this a lot, so it would be better to remember this part. So as the first example, so let's say solve the initial value problem. Initial value problem is a differential equation and initial conditions. We call initial value problem. So y double prime minus 6y prime plus 8y equals 0, along with y0 equal -2 and y prime 0 equals 6. So if you get a problem like that, first thing we do is we write the characteristic equation. That's easy to write. You replace the derivative by lambda powers, right? So the characteristic equation is simply lambda squared minus 6 lambda plus 8 equals 0. We can factor this easy just by factoring out the quadratic formula. So I'm just going to factor this easy. So it is lambda minus 2 and lambda plus lambda minus 4. Lambda minus 2 and lambda minus 4. So that means the solutions are lambda equal 2 and 4. You can see that these are two real distinct that means it's the first case. So the general solution is given by y equal c1 e lambda means 2x plus c2 e lambda means 4x. Now what we can do, so we know the general solution now. We need to use the initial condition to find c1 c2. Okay, so using the initial conditions, we have y 0 equal -2. So that means we're going to plug in that. So that means it is -2 equal c1 plus c2. I'm going to call this equation number 1. Now we have to use the derivative. So that means we have to take the derivative of the differential equation. So the derivative is dy prime x, which is equals to 2c1 e2x plus 4c2 e4x. That's easy to take the derivative. Now what we can do, we can use the condition again. So we can use y prime 0 equals 6 now. If you use that 6 equal, we're going to get 2c 1 plus 4c2. What we can do, we can divide this one by 2. So you can, if you divide, you're going to get this. The easiest way to solve these two equations is you can subtract. If you subtract one from the other, you can see c1 get cancelled. So that's the easiest way to solve this. So we can do that. So let's do that. By 2 minus 1, you're going to get c2 equal 5. And what you can do, you're going to plug in that value to the other equation. Then you're going to get c1 equal -7. So the solution is y equal 5 e to the 4x minus 7 e to the 2x. So that's the solution to the initial value problem. Very simple. So let's do another problem. Find the set of fundamental solutions. Find the set of fundamental solutions and the general solution of the general solution of y double prime minus 8 y prime plus 16 y equals 0. So let's do that. Problem is similar. We're going to find the characteristic equation first. The characteristic equation is lambda squared minus 8 lambda plus 16. We're going to factor. This is easy to factor. This is lambda minus 4 times lambda minus 4 equals 0. So the solutions are lambda equal 4 and 4. We write it like that just to exaggerate the repeat. So the real repeated, repeated. The two solutions are y1 equal e to the 4x and y2 equal x e to the 4x. Just to see whether this form of fundamental set of solutions, we need to check whether they are linearly independent. What we can do is we can use the Wronskian test here. So we can do the Wronskian test to check whether they are linearly independent. To check whether they are linearly independent. To check whether they are linearly independent, what we can do, we can check the Wronskian test. So W y1 y2. So y1 y2 y1 prime y2 prime. So let's plug in. So it's e to the 4x x e to the 4x 4e 4x, and take the derivative. Here we're gonna get two terms. First derivative of x, so you're gonna get e to the 4x. Next derivative of the other term, so you get 4x e to the 4x. Now you're going to take the determinant. So what we can do is we can make some simplification. I'm going to show you some tricks here. When you have determinant, you can always take a common factor out from a row or a column. So you can see that e to the 4x is common in the first column, so I'm going to take it out. And also e to the 4x is again common in the second column, so I'm going to take it out as well. So if you do that, you only get 1 4 here. You get x, and then you have 1 plus 4x. That's what you get after you take the common factors out. Now it is very easy to simplify. So you can see that this is simply e to the, when you multiply, you're going to add the index. So here you're going to get 1 plus 4x minus 4x, the determinant. This get cancelled. So you simply get e to the 8x, which is not equal to 0. That means in general, that means y1 and y2 are linearly independent. So y1 and y2 are linearly independent. And hence you can see y1 and y2 form a fundamental solution. Form a fundamental set of solutions. Good. So the general solution is y equal c1 plus c2x e to the lambda 1x. So if you plug in, you can c1 plus c2x e to the 4x. You can write it like this, or you can distribute, and you can even write it like that. So you can write any form, both are okay. Yeah? So that's the general solution. Good. So let's do another one from the third case. So the example, find the solution of y double prime minus 6y prime plus 13 y equals 0 with y0 equals 0 and y prime 0 equal 10. Approach is very similar. We start with the characteristic equation. Characteristic equation is simply lambda squared minus 6 lambda plus 13 equals 0. I'm going to do a different way now. We can directly use the quadratic formula. Instead, what I'm going to do, I'm going to use the completing square method. So we use the completing square method. Completing square method. So we can use the completing square just to see, like, how it's going to work. So we can take the half of the middle term, that means negative 3. So that means we can write this one as lambda minus 3 squared. Once you do that, you're going to get 9. But we have 13, that means there are 4 left. Now we can write this one as lambda minus 3 squared equal negative 4, which is 4 times I squared. Now we can take the square root. Once you do the square root, lambda minus 3 equal plus or minus 2i. It's going to give you lambda equal 3 plus or minus 2i. Perfect. So you can also get the same formula, same result from the quadratic formula easily. Now we have the 2, that's the alpha, and this 2 is the beta, just that. So we have alpha and beta. So we can write the solution now. So the general solution is y c1e alpha equal 3, so 3x cosine beta equal 2, so 2x plus c2 e 3x sine 2x. So you can see that there are no complex numbers in the solution. It is just real. C1, C2, we write it like that. So the goal is to find the C1, C2. By finding the general solution, that's it. So now we can use the initial condition. So we can use y0 equals 0 now. That's going to give you 0 equal. So let's plug in 0 everywhere. So we have c1 e to the 0 cosine 0 plus c2 e to the 0 sine 0. But we know few things. For example, we know that cosine 0 is 1 sine 0 is 0. So because of that, this term gonna go away. You simply getting C1. That means C1 equal to 0. So if C1 equal to 0, we can simply remove that from the general solution. That means the solution is now it is simply y equal, because C1 is 0, so that you can remove that, so you only have C2 e to the 3x sine 2x. We don't want to worry about C1 anymore because it is 0. Now what we can do, to use the second condition, we take the derivative. But you can see, if you try to take the derivative with the original term, you have 4 terms, but now we have only 2 terms. So we take the derivative. So taking derivative, so taking derivative, we have y prime equal 3 c2 e to the 3x sine 2x plus 2 c2 e to the 3x cosine 2x. Now y prime 0 equal 10 gives you that 10 equal 3 c2 e to the 0 sine 0 plus 2 c2 e to the 0 cosine 0. And you can see that again, this is 0 and this is equal to 1. So you simply get into c2. In other words, c2 equal 5. So this says that c2 equal 5. So the solution to the initial value problem is, the solution to the initial value problem is y equal 5e3x sine 2x. So that's the solution to the initial value problem. So let's do one last problem, like a different type of problem. What I'm going to give, I'm going to give you the solution now. Ask you what is the differential equation. So suppose y equal 5e negative 1/2 t cosine 3t minus 7e negative 1/2 t sine 3t is the solution of a differential equation. Find it. So find the corresponding differential equation. So how you do this kind of problem? So you can first see that this is a one of the family of form. That's a third case. So you can see what is the alpha value and what is the beta value. Okay, so the alpha is negative 1/2, beta is 3. So that means you can write the lambda. So the form suggests that, the form of the solution suggests that lambda is simply 1/2 plus or minus 3i. So lambda has to be of this form, because if we have this, then we can write it like that, so that we can go backward. Now since we know the lambda, we can write the characteristic equation. So the characteristic equation is so what we can do, we can subtract this lambda. So it's lambda minus the first value times lambda minus the second value. Now what we can do, we can multiply inside by the negative sign, we can distribute the negative sign, so you simply end up getting lambda plus 1/2 minus 3i lambda minus 1/2 plus 3i equals 0. That's what we get. Now what we can do, we can simplify this further. We can distribute it and try to find an expression. So we have, if you distribute, you're going to get lambda squared plus lambda 1/2 plus 3i, and then you have also 1/2 minus 3i. Those are the lambda terms, and also get 1/2 minus 3i 1/2 plus 3i, everything equal to 0. And you can see that these two terms get cancelled, and this is like x minus y, x plus y, the difference of squares. So if we do all, then you're gonna get lambda squared plus lambda 1/2 is lambda, and here what's gonna get by the difference of squares, you're gonna get 1/2 squared minus 3i squared equal to 0. So you're gonna get 1/4 plus, because I squared is -1 with the negative sign plus 9. So that means if you add them, you're gonna get 36 plus 1, that's means 37 over 4. So your differential equation gonna be simply the characteristic equation gonna be lambda squared plus lambda plus 37 over 4 equals 0. In other words, if you multiply by 4, it is 4 lambda squared plus 4 lambda plus 37 equals 0. So then we can write the corresponding differential equation. We can replace the lambda by derivatives. So the corresponding differential equation is the corresponding differential equation is 4y double prime plus 4y prime plus 37y equals 0. That's the differential equation. Now what we want to do, so if you want to find differential equation, we are done, but we can do something. I'm going to show you some other things. For example, if you want to find the corresponding initial conditions, what we're going to do, we can start with the solution and plug in some condition. Okay, so this extra step. So to find an initial condition, simply set t equals 0 in the solution. So that means y is 0 equal, so we have 5 e to the 0 cosine 0 minus 7 is 0 sine 0. This simplifies very well and you get 5. So that's the one condition that you may have had at the beginning. And also what we can do is we can take the derivative of the differential equation, plug in 0 again to find another initial condition, or we can find a different kind of condition. We can find what we call a boundary condition. We can plug in another value other than 0. So for example, to find another condition, we're gonna set t equal pi over 4 or pi over 2. So we can set the, why we do that, because you can see that that's gonna simplify the equation a little easier, because we have a cosine term that's gonna go 0. So that's why we pick these values. So you can pick pretty much any value. So if you do that, y pi over 4 pi over 2, which is equals to 5e negative 1/2 pi over 2 cosine pi over 2 minus 7 e to the negative 1/2 pi over 2 sine pi over 2, and then you can see that this is equal to 1, this is equal to 0. It's gonna go away, so that means you end up getting negative 7 e to the pi over 4. So that means thus you can use as the second initial condition, not initial condition. You can see that this is not an initial, this is like a in a corner. So we had one condition at the beginning, 0, that's what we call initial. This is like pi over 2. So this kind of condition are what we normally call a boundary condition. That's a boundary corner. Okay, so so this new condition y pi over 2 equal negative 7 e to the negative pi over 4 is called a boundary condition because it's given at a boundary. So this condition is called a boundary condition. Boundary condition. Thus the corresponding boundary value problem that's the corresponding boundary value problem is given by 4y double prime plus 4y plus 37y prime, 37y equals 0, along with y0 equal 5 and y pi over 2 equal negative 7 e to the negative pi over 4. So if you try to solve this differential equation, you end up getting that solution. Okay, so let's have a small note about how to find another initial condition. To find a condition with a derivative, first take the derivative of the solution. First take the derivative of the solution and set t equals 0, to obtain another initial condition, to obtain another initial condition. That's how you can get another initial condition, and then you can form a initial value problem. So this is like, so you can either have another boundary condition, or you can have another initial condition, first taking the derivative and then plug in t equals 0. So you can find another initial condition with a derivative. Good. So that's the end of the constant coefficient differential equations.